I'm Terry Borroz, a software engineer in the Defense Aerospace Group at Teradyne. I've been involved with Teradyne's support for boundary scan since it became an IEEE standard in 1990. Boundary scan is a method widely used for testing complex electronic circuits, and recently it has also been popular as a means for flash programming. In this session, we will talk about boundary scan capability available on Teradyne digital instruments and systems, and get a closer look at Teradyne's different instrument options that support boundary scan. So first, a very brief introduction to what boundary scan is. Boundary scan is a test methodology based on standardized test support circuitry that can be included in ICs. It was standardized as IEEE 1149.1 in 1990, and it provides direct control and observation capabilities at the pins of an IC. This circuitry is accessed using serial data transfer through a 4 or 5 wire data port called a test access port, or TAP port for short. The design allows multiple boundary scan ICs to be daisy-chained together so that all the boundary scan ICs on a board can be accessed from a single 4 or 5 wire connection. The initial intent of this standard was to enable more efficient tests for board-level faults. And the classic example of what this is good for is interconnect testing. So it turns out that if you have a board full of boundary scan ICs, you can run software that automatically generates a test that can detect and diagnose shorts, opens, and stuck pins anywhere among all the interconnections between the boundary scan ICs on the board. This is done by repeatedly driving different patterns of values on all the boundary scan output pins on the board, and then looking to see if the input pins connected to them see the right states. The picture on this slide illustrates how it works. This and other similar techniques are now in wide use, but although boundary scan was designed for production board test, it turns out that it has also become common to use it to do flash programming. I'm talking about writing data into flash memories that don't have their own boundary scan by using access provided by adjacent ICs that do have boundary scan, as shown here. Doing this is inherently slow. It usually means that you have to do several full shifts through the long shift path through these adjacent boundary scan ICs for each byte that you want to write into the flash. But even with that drawback, it's popular. This is because sometimes it's the only easily accessible way to reconfigure flash after a board has been built. Because this process is so slow, flash programming is the application most in need of careful instrument design that is optimized to run as quickly as possible. Now, although just controlling the tap port is enough for doing a lot of testing, like the interconnect tests I just mentioned, it's important to remember that you can usually do a better job of whatever your objective is if you can also control the edge signals of the UUT. We usually call these signals PIOs for parallel inputs and outputs. And in many situations, you already have tester channels connected to them because you need that for other non-boundary scan tests anyway. There are two ways to connect to PIOs during a boundary scan test. The traditional way is to directly wire them to tester channels, as I just mentioned. We refer to these as direct PIOs. But note that the fact that we're working with boundary scan means that an alternative technique can be used in some situations. What you can do is wire the UUT edge signals to additional boundary scan ICs that you position near the UUT. So you wind up with something that looks like this. You can see here that we've placed external boundary scan ICs around the UUT to connect to its edge signals. We call these connections scanned PIOs. The test generation software can make use of them by conceptually treating them as if they were part of the UUT. This idea was initially developed by benchtop boundary scan vendors, and all the boundary scan companies now sell benchtop pods containing boundary scan ICs to support this. So you can do this either with individual ICs as shown here, or you can do exactly the same thing using vendor pods built for this purpose, like this. Now, let me shift gears for a moment and talk about Teradyne's support for boundary scan. We used to develop tools to generate boundary scan tests. This was the Victory software, mostly developed back in the 1990s. But we eventually got out of that business. Boundary scan test generation is now mostly handled by third-party companies that specialize in boundary scan. Companies like JTAG Technologies, Asset Intertech, Acculogic, and Corellis. These companies make their own software to generate boundary scan tests and execute it on their own hardware. Test development usually happens in a benchtop environment, where this hardware typically takes the form of small pods positioned near the prototype. Similar pods are used for FPGA programming during development. An example is shown here. The production test environment is different from the development environment, with the UUT typically connected to production test equipment, such as the Spectrum system shown here. Integrating the benchtop hardware used for test development is difficult in this setting. To address this issue, Teradyne has developed a software layer called TERBSR for Teradyne Boundary Scan Runtime, so that the boundary scan companies can straightforwardly run their tests on our hardware. This is good for us, of course, because it makes it easy to use our testers for boundary scan. It's also good for our end users because it gives them a way to run tests developed using their customary boundary scan tools on their existing Teradyne test systems without putting extra hardware in the fixture. And it's good for the boundary scan companies because it lets them run their tests in production as the end users prefer on existing production test systems without additional hardware or pods. Teradyne offers two instrument families that can run boundary scan tests using TERBSR. Our DI series digital instruments can be used for this. These are VXI general purpose digital test instruments. They are not optimized for boundary scan, but they can execute most boundary scan tests pretty efficiently. And one notable feature is that they have custom pin drivers with a wide voltage range and damage protection. In addition, we offer the high-speed subsystem. There are many individual instruments within this family that can be used for boundary scan testing. These are all PXI instruments. They have configurable firmware, and many have available firmware that is optimized for boundary scan. Their pin drivers are not as generic as those on the DI series. They use naked FPGA outputs with clamp diodes, and they only support a limited set of voltages. So I'll briefly highlight some of the advantages of these instrument families. In terms of raw speed, the high-speed subsystem can provide much higher throughput than the DI series. The high-speed sub uses custom firmware which implements a high-speed boundary scan processor with features especially optimized for fast flash programming. These include double buffered DMA loading of precompiled instruction streams. This system can get within 10% of the device-limited test time. This is the theoretical minimum time to do a given flash programming task, limited only by the constraints imposed by the UUT. In terms of available voltages, the DI series clear advantage. Pins are individually programmable for over a huge range, plus 30 volts. Compared to this, the high-speed sub-volts are limited, but they are good enough for most situations. There are 4 single-ended voltage choices, 3.3, 2.5, 1.8, and 1.5 volts, plus LVDS differential. Voltage configuration usually affects an entire HSSub instrument, although there are some instruments where the available pins are split into sections where each section has its own voltage. Because of this architecture, it is almost always the case that all taps must use the same voltages when using HSSub instruments. When planning how to connect to a UUT, both DI series and high-speed sub-instruments offer a lot of flexibility, but there are some differences to keep in mind. In many ways, DI systems are the easiest to think about. This is because adjacent DI series cards get combined together into a big virtual instrument. And once you do that, you can now assign each individual tap pin and each PIO pin anywhere within this entire field of pins. So you have maximum flexibility in how you lay out your fixture. With the high-speed sub, there are more constraints. For example, all taps must be on the same instrument, so you have to remember that when planning. Also, if you need multiple PIO voltages, you usually have to use multiple instruments and decide which ones handle which voltages and wire things up accordingly. Some HSSub instruments can do one thing that DI instruments cannot do. We now have firmware available that lets you configure some HSSub instruments to emulate boundary scan ICs. So as I mentioned before, you can get scanned access to UUT edge pins by connecting to boundary scan ICs placed nearby, or alternatively, you can achieve the same result by using HSSub instruments, since they can be configured to emulate boundary scan ICs. Now, also on the subject of PIO access, I just want to take a minute here to let you know that we've done some recent work so that you can now additionally use a DI series virtual instrument to provide direct PIOs in a boundary scan test where the taps are controlled by an HSSub instrument. To do this, you have to hook things up as shown in this sketch. All of the instruments have to be controlled by the same PC. You can use high-speed sub-instruments as you normally would, but then you can also connect an additional DI virtual instrument to provide additional direct PIO connections to the UUT. This can be especially useful if you have a couple of UUT signals with uncommon voltages, or if you just need some way to provide extra tester connections because you have a very high edge pin count. Now let me go through a few slides that explain the high-speed sub-instruments that support boundary scan. There is a whole family of high-speed subsystem instrumentation with a growing number of instrument types and firmware options that can be used for boundary scan testing. Each supported HSSub instrument type has selectable firmware options that differ regarding available voltage levels, support for scanned PIOs or not, and which pins are capable of controlling tap ports. You can combine multiple different HSSub instruments in the same test. You can mix and match as needed. Note that only one instrument can drive tap ports on the UUT. All additional instruments in the test can only connect to UUT PIO signals. So here are the high-speed subsystem instrument types that we support. The top 4 rows are similar, and they all support variations of our standard high-throughput boundary scan firmware. The top row is the original HSSub instrument that was supported by TERBSR, the LVTTL 6020 instrument. The second row is just a new spin of that same instrument with new front panel connectors because they stopped making the old connectors that we used on the 6020. The third row, the E-digital instrument, is identical to the original 6020 in row 1, but with different physical packaging that only brings out 76 pins. So the top 3 rows are all variations of the same instrument. Then there is the 8G hybrid 6140 on row 4. This is a new instrument with a new generation FPGA, but once again, its boundary scan implementation is very similar to the rows above it. The last row, the hybrid 6040 instrument, is usable with boundary scan, but only to provide direct PIOs. Here are the voltage levels that can be supported by all these HSSub instruments. You can see that all types can handle 2.5 volt and LVDS levels. Most types can also handle 3.3 and 1.8 volt levels, and many can also handle 1.5 volt levels. So here's a summary slide that recaps some of the factors that I've just gone over that might make you prefer to use one instrument type versus another. As noted, the high-speed subsystem is by far the fastest platform. The DI series supports a much wider range of voltage levels, and the HSSub is the only platform that can provide scanned PIOs. Also, note that HSSub is a newer platform, so there is more active development and new features coming in the high-speed subsystem family. As I had mentioned before, with HSSub instruments, tests can be compiled for maximum execution speed. When should this feature be used? The general rule is to compile when creating very long sequences of activity. In practice, this makes sense when programming, verifying, or blank checking flash memory, and it's usually not useful elsewhere. It provides only minimal benefit, if any, for short tests like interconnect testing, because short tests execute so quickly that the improvement is negligible compared to other overhead times. And furthermore, compiled execution is a go-no-go technique, so it's not suitable for tests where diagnosis is important, like interconnect test. By the way, note that some boundary scan tool sets manage the use of compiled execution automatically, so that the end user has no control over when it's used. For example, they might automatically compile as an extra step the first time a new flash sequence is executed, and then use that precompiled sequence thereafter. So here's a final slide that summarizes what TERBSR offers. You can use it to execute boundary scan tests generated by any of the boundary scan vendors shown here, with full vendor debug and diagnostic capability on either DI series or HSSub hardware, all without requiring any vendor pods when connecting to the UUT. And note that Teradyne also has implemented its own SVF interpreter, so that any test sequences specified in the SVF language can also be executed. That concludes the boundary scan presentation. Thank you all for attending. Please submit any questions you might have, as this will be followed immediately by a live question and answer session.
Hello, everyone. Thanks for joining us. I'm Tara Marchetti. I'm a quality engineering manager here at Teradyne, and I'm here to pass along any questions that you have to Terry. So if you do have any questions around today's presentation, please put them in the comment section. Terry, thank you for being here for this. It looks like we already have some questions that have rolled in, so let's dive right into it. There's a question around the faster clocking speed you can realize depending on your controller system. So can you compare the DI and high-speed sub clocking speed, since they do have different PCs?
Yeah, so they can both run at clock speeds up to 50 megahertz. So in terms of actual clock speed, there's no difference between the two platforms. However, the high-speed subsystem is optimized for more throughput. So if you're doing a really long sequence, there will be, clocks going out at 50 megahertz, and then brief periods of hiccups. You'll have a burst of 50 megahertz, and then it'll wait a while and do another burst and another burst. And those wait times are kind of much, much smaller if you're on the HSSub platform because of the precompiled execution streams and so on that I mentioned in the presentation.
Great, thank you. I think that answers that well. Next question here. What is the TERBSR code difference when you're using a DI versus a high-speed sub? Can you develop on a DI and then transfer it to a high-speed substation?
You can. There are some TERBSR features that are only supported on high-speed subsystem. The ones having to do with pre-compilation, for example, you can't do that on a DI. The underlying hardware does not support it. So, for all of those features that can be executed on either platform, you could develop on either one and then straightforwardly port that to run on the other. If you really want to take advantage of the features that the high-speed subsystem provides, then you sort of have to develop on the high-speed sub for that.
Right. Okay. We've got another question asking if it's possible to get a copy of this presentation. I'll jump in here. This will be available on our eKnowledge site. And Terry, can you provide more details on the fast flash programming capabilities for high-speed subsystem?
Well, I think sort of roughly what we did there was we designed the system just to be able to go as fast as possible in terms of eliminating any throughput limiting stuff to the extent that we could. There was, in a previous TIM, I gave a presentation about the architecture of the high-speed subsystem hardware underneath that allows this to happen with the double buffered program loading, the configurable firmware architecture, and things like that. That was like another 20-minute presentation, and there's not too much time to go into that here, but I believe that the slides for that presentation are somewhere on eKnowledge. I think
those should be up on eKnowledge as well. Yeah.
Yeah.
Great. Okay. Another question here: which boundary scan companies are able to use TERBSR to execute their tests on Teradyne hardware?
Yeah, so let's see, the four companies that have kind of fully qualified their products with TERBSR are JTAG Technologies, Asset Intertech, Acculogic, and Corellis. And we're open to working with other companies as well, but those are the ones who've worked with TERBSR so far.
And those are qualified. Those have actually
Yes.
been put into implementation. Great.
Yep.
Another question coming in. I know there are other standards in IEEE 1149 family in addition to the basic 1149.1 boundary scan standard. Can TERBSR support any of those related standards?
So regarding the related standards, some are very similar in architecture to 1149.1 and some are not. TERBSR is an 1149.1 focused thing, so it should be able to support the ones that are similar. And of course, running with one of these other standards depends on whether the boundary scan company that you're using to generate the tests supports that standard as well. So far, no customers have actually used any of these related standards at all with this, to my knowledge. So far, we've only had preliminary discussions with these boundary scan companies about supporting other related standards. Of those standards, 1149.6 is by far the most important. It's kind of an extension of .1 to enable you to do the interconnect test type techniques that you use with .1 with capacitively coupled nets. And this is used by communication companies like Cisco and companies like that who have these kind of SerDes capacitively coupled things. We believe that it should be possible to test things like that using TERBSR from our discussions with some of the boundary scan companies. But like I said, this hasn't really been tried yet. So I think it'll work, but we'd like to try it. So if you have an application, approach us and we'll talk about it.
Reach out, absolutely. Okay, next question. Are PIOs digital or hybrid channels? And if they're hybrid, what kind of analog measurements are possible?
Let's see. So the PIOs, all of this boundary scan stuff is a digital technique. And so when I talked about PIOs there, I was talking about additional digital signals that you can connect to the UUT. These can be, sometimes there are just a few signals that you want to have in specific states to enable other things. Other times they are things that participate in interconnect testing and stuff like that. But this is all digital. These are not. I'm not talking about analog signals there. I guess I could say if there are analog things that you have to set up while doing a test, I suppose you could coordinate some other instrument in your test system to configure those while you then run boundary scan. But that's sort of beyond the scope of what TERBSR does.
Right. Great. Let's see. I don't see any more questions coming in here. We had a nice stream of them. That was great. Thank you, everyone, for joining today. I believe that concludes our event. I hope everyone will join us next time. And thanks again, Terry.
Thank you.